So we've talked about self-contained devices. We've talked about through beam or source receiver type devices. Something they would have in common is lensing. All these photoelectrics need lensing in order to accomplish what they do. Our basic circuits would only operate over a very short distance because of the wide angle of the light emitted from the source and the light viewed by the receiver. With lensing, we're able to focus that beam of light and result in a much more defined beam and increased sensing distance of our circuit. The angle of this defined beam is establishes the field of view, actually. You can think of field of view in a way, a simple way, like a garden hose with a nozzle on the end of it. As we adjust the spray, we see that we can get a long range using a narrow beam, whereas we can widen the spray out to see a wider field of view, but our distance decreases. Diffused and transmitted beam sensors typically have field of view in the range of 1.5 to 7 degrees for maximum distance and ease of alignment. Other sensors with beams that diverge greater than 40 degrees are generally referred to as wide-angle sensors. Sensors with beams that converge are typically referred to as fixed focus sensors. When you think of fixed focus, basically you've got a single device sending out a beam of light at a specific angle, and you have a receiver looking for that modulated beam of light at a specific angle. So its focal point is a certain distance from the sensor itself. A lot of these might be 100 millimeters. That's a very typical of a fixed focus device, 100 millimeters or closer. Field of view versus ease of alignment, that's a discussion we can have. A sensor with a 1.5 degree field of view has a spot size of 3 inches at about 10 feet away. That makes alignment more sensitive. A sensor with a 3 degree field of view has a 6-inch spot at 10 feet, making alignment easier. So typically if you're working with a reflector, the more light you're putting out there, the wider that field of view, the easier it is to hit your reflector. Another consideration when you're talking about field of view is sensor crosstalk. That occurs when you have sensors mounted adjacent to each other and they're close enough to be within the other sensor's field of view. That's why it's very important to understand the field of view of the sensor you're working with. Typically are requirements posted with all the information on your sensors telling you how to mount them, how close together they can be mounted, and so on. But it is definitely a consideration you want to keep in mind when you're mounting sensors in a very close proximity to one another. Now that we've determined the field of view of our sensor, let's talk a little bit about the effective beam. That's how the beam comes out of the sensor at its particular angle and is projected out into the area you're trying to sense. If you take, for instance, a photoelectric retroreflective sensor with a 3 degree field of view, at 10 feet it's going to project a 6-inch diameter circle. That's basically a typical retroreflective sensor that would require a reflector as a target to operate. When we talk about the effective beam, we're talking about how much do I need to break that beam in order for it to operate properly, to get an output. So if you look at a typical sensor, you've got the light coming out at its 3 degrees, it's angling out towards your reflector. Depending on the distance of what I want to detect is going to determine how much effective beam I have. For instance, if I'm only about 2.5 feet away from that, I might have a effective beam of about 1.5 inches. So what does that mean? That may mean that I need to have at least a target that's going to cover that 1.5 inches to block enough of that beam so that the reflector doesn't get enough light and reflect it back to the sensor in order for me to think there's nothing in front of it. So that is something you have to worry about a little bit. Light going around your target, still hitting the reflector and coming back and being detected, not allowing the device to have an output. Just want to make sure you've got a big enough target to block enough of the beam to get the output you're looking for. If I put my reflector at 3 feet away, my 3-inch reflector at 5 feet away from the sensor, then your effective beam is 3 inches. Our original target of 1.5 inches is now not sufficient to break the beam because you've got enough light going around it that it's just not going to work. It's not going to break the beam. You would need a target at least 3 inches in order to break that effective beam. Following that logic along, if you take a 3-inch reflector 7.5 feet away from the sensor, your effective beam remains 3 inches as limited by the size of the reflector. Note that the field of view of the sensor at this distance is 4.5 inches, which is larger than the size of the reflector. But you're limited by the size of the reflector, so a 3-inch target would still block enough of the beam that you would get an output from your sensor. And following the same logic along, as we move out farther to 10 foot, as we discussed earlier, you've got a 6-inch diameter circle. I'm using my 3-inch reflector, but my effective beam is still only 3 inches because of the reflector size. So I still only need a 3-inch target to block that reflector and get an output from my sensor.